And I'm presenting a work on learning cognitive features from gaze data for sentiment and sarcasm classification using CNNs. So we have been following this kind of research where we sort of try to show that incorporating cognitive data for different NLP problems actually helps solving the problems better. So this is one piece of incremental work which, sorry for that. Okay, that's better. Yeah. So here we this is an incremental work that in which we try to show that the features from the cognitive data could be learned automatically using deep neural network. So a bit of a background. So recently in last year's ACL we presented a couple of papers on how cognitive data derived from the eye movement patterns of annotators could help solve classification tasks like sentiment analysis and the sarcasm detection better. The current objective here is we give the onus of feature engineering to CNNs. And as we all know, deep neural networks have been proving very effective for many NLP problems. This work is already a year old. I'm sure the state of the art has advanced a lot. But the key findings are twofold here. One is automatically learning cognitive features is possible using deep neural network, and the second is addition of this kind of cognitive features to with textual features would help solve classification problems better. So that holds for our experiment. So that's what we want to pass on through this presentation. Okay. So why do we need such approaches? As we all know, sentiment analysis and sarcasm detections are not so easy problems to solve because they are nuanced at different levels of linguistic difficulties, from lexical to syntactic to semantic and pragmatic level. They are all nuanced. So to give you some example of why the problems are difficult, just look at these examples. Sentiment analyzer should face trouble because of the fact that the opinionated text can contain implicit sentiment, as shown in the example, or sarcasm or irony or thwarted expectations, which throw enormous challenge to these systems. And existing work towards addressing these challenges leverage stylistic features or smileys or extra linguistic information that should be present in the text. But in the absence of such information, it often becomes difficult for systems to sort of address these challenges. So our general approach, we have been using cognitive features derived from the eye movement data of annotators. Obviously, one needs to have the eye movement data available for such kind of systems to be in place. We have workarounds for bypassing the eye movement data during test time also, but this work takes eye movement data during testing. How feasible it is? It is feasible because inexpensive eye tracking devices are sort of available now. They are close to a reality, so probably in future we'll have Android devices and mobile phones with cameras that could be used for tracking the eye movement patterns of the readers, and we could use that information in our classification setting. Okay. So this is how the eye movement data on the piece of text looks like. This is the eye movement data is from one annotator. As you can see, the blue dots represent the fixation points. These are basically longer stay of gaze on the position of the wrist. And the jumping between two fixations is called saccades. So if one has to represent it in a sort of a graph, it would look like this. The x-axis represents the word IDs here in a sequential manner, and the y-axis represents the sequence in which the words are accessed or fixated. So as you see, the first sentence here is a sarcastic one, and by sarcastic it means it has some kind of situational disparity by theory, which is called as incongruity, and this incongruity attracts longer fixations or multiple regressive saccades. So users generally move their eye positions back and forth between two incongruous phrases. So this is the motivation behind why eye movement data could be useful for classification setting where there is the classification is nuanced by such kind of subtleties. So why CNNs? Obviously we know they have been quite good in extracting spatial features. For example, in image classification for detection of contours, edges, they are proving to be pretty good. We thought same kind of networks could be useful for extracting gaze subtlety as well. For example, a longer regression from in between two incongruous phrases. So that's the motivation behind choosing CNNs, which led us to design this kind of neural network architecture, which is on top of the architecture that has been widely used for sentiment classification. This network has two components. One is for text feature extraction and one is for gaze feature extraction. In text side, as we all know, it's a well-known thing that people use embedding layers of two kinds. One is static, one is non-static, to extract balanced, tuned set of embeddings, which could be fed to the convolution layer, and from the layers we could get local features. And on top of that, a max pooling layer ensures that the global features from the text are extracted. But here the addition is that we have a gaze component, which is basically eye movement data coming from different participants stacked on each other in a matrix representation. Please look at the paper for details. So here, basically what we are doing is we have two channels such as fixation channels, where the fixation points are represented in the rows of this matrix, and we have Sarcasm channels where the position of the fixations are presented in the form of a matrix. On top of that, we apply a 2D convolution as opposed to the 1D convolution that you see for the text side. The 2D convolution application ensures that different gaze points coming from different participants are taken into consideration while extracting spatial features. So this would ensure that if many people have similar gaze tendencies on a piece of text, that should be incorporated in the features. So once the convolution filters are applied here, we pass them to again the max pooling layer, which is also 2D in nature, which gives us a set of features from gaze side as well. And once we have these two kinds of features, they are merged together and passed through the classifier. So as I said, the static and non-static embedding channels ensures that there is a balance between highly tuned set of embeddings, task-specific tuned embeddings, and static embeddings which are not tuned at all as per the task. The fixation and Sarcasm channels ensure that we have all sorts of different forms of complexities addressed here. For example, fixation channel ensures that lexical complexities are taken into account. Sarcasm channel will ensure that syntactic and incongruity related complexities are taken into account. But there is a fundamental problem with such a design, that it depends on the ordering of the gaze data. So if we change the order during testing, it would probably result in a different kind of, it would probably behave differently. So that's a problem we are addressing. One of the solutions is you try all the combinations of ordering in a brute force manner, but that's not scalable. Right now, as of now, the training and testing ordering are sort of preserved. We use two publicly available datasets that we have released and mentioned in our previous papers. These contain 2,000 different instances for which the annotation size is like 7 to 5 participants per instance. So we have around 7,000 plus 5,000 instances of eye movement data available for the text. So different configuration of experiments could be tried out with the datasets. So one with only the text components being present, and one is only with gaze components, and one is with different combinations of both text and gaze. These are some of the details. I'm skipping for the bit of time. So the results that we got here with such kind of network is, it shows that for both sentiment analysis and sarcasm detection, we are beating the state of the art, and that's a year-old state of the art, I must say. But yeah, so it's consistently outperforming the only text-based approaches, obviously because of the addition of the gaze data. Alongside with that, we observed that in gaze also addition of multiple channels generally tend to help. For dataset 2, we have a little negative result, while we see that the accuracy is better than only text-based approaches. It's not beating text plus gaze-based approaches that we had proposed earlier. Same with sarcasm detection. So the observation here are that we see a clear overfitting for dataset 2 because we are not over-tuning the hyperparameters in our experiments. These are set by trial and error. Yeah, and two important observations here that the effect of static and non-static channel is observed, like the words adjectives such as good and nice are coming close to each other by the help of the non-static channel, and similarly some words like named entities coming close to some adjectives together is not happening because of the presence of the static channels. The fixation saccade channels are also helping. The saccade channels especially are good at handling incongruous instances better. Yeah, so this is one analysis I'd like to spend some time on. So we plotted the output of the feature, output of the convolution layer. This represents the features learned by the network. As you can see, the first sentence here is sarcastic in nature, while the second is not. The features learned by the gaze data, gaze plus text data, actually shows a portion which is more intensified than the features learned for the non-sarcastic text, which shows that sarcasm is actually an intensified negative opinion. So some features are actually being able to capture that kind of intensity if we incorporate the gaze information, while the only text extracted features are not being able to do so. So the red bordered examples are the ones that are classified wrong in our setting. As you can see, there is a clear difference between the text plus gaze features and the gaze features. Probably that's the reason why only with text features the classification was not perfect. And the example 4, I think both the systems did not perform well, maybe because of the fact that it is already a little confusing for humans to come up with the appropriate sarcasm level for this this example. So the system might have got confused. That's why both the system couldn't, even with the addition of case data, they couldn't perform well for the example. Yeah, this is what I said, so I'll just skip this slide. So in conclusion, to conclude, we proposed a CNN-based network to automatically extract features representation from raw gaze and text inputs. On multiple published datasets for which gaze information is available, our system could often achieve significant performance improvements over systems that rely on handcrafted gaze and textual features, and CNN-based systems that rely on text input alone. So analysis of gaze features, the features extracted confirms that the combination of automatically learned features is indeed capable of representing deep linguistic subtleties in text that pose challenges to sentiment and sarcasm classifiers. So some future work. So the midterm work is obviously we have to come up with better hyperparameter selection because all these hyperparameters that we fixed are based on empirical observations, because we didn't want to overtune the hyperparameters on different datasets that we have used. Then the other line of work is to explore the applicability of our technique for document level sentiment analysis. Right now we are only dealing with snippets and small text where incongruity is clearly sort of visible, but when you deal with documents, the flow of document kind of can come into picture as well. That needs to be taken care of. And the third line of track is we want to sort of get rid of the requirement of gaze data during testing. So that leads to a setting where there could be networks which can take gaze data during training just to tune the model parameters, but during testing we might not need them. So that leads to a multitask kind of a setup where you predict gaze as a task instead of giving it as an input. The long-term goal obviously is to apply our framework to related NLP problems such as emotion analysis, text summarization and question answering, where considering textual clues alone will not prove to be sufficient. So this is the website where we have released the data set and resources. Do visit the site. And that ends the presentation. And we have been, so all these different cognitive NLP related works are sort of combined together, and we are publishing it as a monograph, which will be released in December, so watch out for that if you are interested. Thank you.
Thank you for your talk. I think it's a really interesting area of research. Have you guys looked at EEG data in this context, or do you guys plan to look at EEG data?
Yeah, we have plans, but right now we are just sticking to the gaze data because we thought there is a lot more to do with gaze data alone. But yeah, it's an interesting line of work where different sort of activation of brain units could be also taken into account. The only problem with EEG is that during testing, at least you could afford to collect gaze data, but EEG data is difficult to collect during test time. So one has to propose first a method to sort of take into account this kind of cognitive information during training and not require them during testing. So if one achieves that, then obviously easy data can be more useful. That's it.
Thank you.
Welcome.
I have a question over here.
Yeah.
This is really interesting. My question is, how do you think, so I work on sarcasm detection and sentiment, and I'm just wondering, how do you think this could be possibly scalable, that we could leverage this sort of information in text-based analysis, right? Because we need to be able to get that data, right?
Yeah. So one is to ensure that, see, so whatever we have data we have worked with, they are pretty shallow in nature. So you could assume that in settings where low-cost devices are available, such data can be harnessed and used without, because we are not going into microseconds and pupil and all those kinds of information here. So as long as you capture the coordinate points in a very shallow manner, you don't need intra-word transition information, things like that. So as long as you have this kind of shallow cognitive information, you have access to that, you can pretty much use low-cost eye-tracking devices to solve these kinds of problems. The second line of action is obviously train using eye-tracking data and don't need it during testing time. So that's where this multitask kind of setup could be very useful, where your network would have shared parameters. Those could be tuned using gaze, but they don't require gaze data to be available during testing. So that's something that could make these things quite scalable. Thank you.